In this video, I want to do the example of solving. So let's solve x double prime plus 4x prime plus 13x equals 0, subject to the initial condition that x of 0 is 7 and x prime of 0 is 2. So this is again a second degree linear homogeneous with ODE with constant coefficients. So this is kind of a silly way to go about doing this, but it's good practice for Laplace transforms. So let's solve. So let's take the transform of both sides. I want to just write it out in some detail here. So we're going to take the transform of both sides. And the Laplace transform of x double prime will be s squared capital X of s minus s times little x of 0 minus x prime of 0 plus 4 times the Laplace transform of x prime. It will be s capital X of s minus little x of 0 plus 13 capital X of s. And that's going to be equal to the Laplace transform of 0, which is 0. Okay, now let's plug in the values that we have, and let's simplify all of our terms. So we're going to have s squared plus 4s plus 13 times capital X of s. And that takes care of that term, and that term. We're going to have a minus s times x of 0, so that's minus 7s. Minus x prime of 0 is minus 2. And then 4 times, let's see, x of 0 is 7, so 4 times minus 7 will be minus 28. This is going to be equal to 0. And what we're going to do then is let's add 7s plus 30 to both sides. And then we're going to divide both sides by s squared plus 4s plus 13. I don't really need the parentheses there. Okay, now we want to take the inverse Laplace transform, and so what we're going to do is we're going to complete the square in the denominator. So again, we go back to our old friend of completing the square. So if we have s squared plus 4s plus 13, we want to think about what do we want this coefficient term to be so that it's a square. We want it to be 4. So there's two ways to do this. I like to just add 4 and subtract 4, and in that way we're adding 0, and then everything is completely balanced and life is good. Or you can just think about, if I have 4 here, what would have to be remaining, right? And it's of course s squared plus 4s plus 4 plus 9. So this is going to turn out to be the quantity s plus 2 squared plus 9. So we have 7s plus 30 over the quantity s plus 2 squared plus 9. Now, if I had an s plus 2 in the numerator, this would be very nice. We would be all set because we know if we look at our table of Laplace transforms, what does this kind of look like? Well, this kind of looks like rules number 15 and 16, which say that if you have the Laplace transform of e to the at cosine of kt, for example, what you're going to get is s minus a over s minus a squared plus k squared. So clearly our k is 3, and our a is going to be negative 2. But if we just have an s upstairs and not an s minus a, this isn't true anymore. And what we need to do is figure out how do we put an s plus 2 in the numerator here. Okay, so how do we put an s plus 2 in the numerator? So what we're going to do is I'm going to put an s plus 2 in the numerator, and then I'm going to subtract 2. And then we'll just simplify what happens. This is basically the same trick twice, right? If we added 0 and we're adding 0, multiplying by 1 gets all the love, but adding 0 is very useful as well. So this is going to be divided by the same denominator, s plus 2 squared plus 9. So this is going to be 7 times the quantity s plus 2 minus 14. So minus 14, so 2 times 7 is 14, plus 30. So all over s plus 2 squared plus 9. So this is going to be 7 times s plus 2 over s plus 2 squared plus 9 plus 16 over s plus 2 squared plus 9. So we're going to need both rules 15 and 16. I just wrote down rule 15 at first. So this is actually rule 15 according to our handout. Rule 16 is for the Laplace transform of e to the at sine of kt. And it turns out that that's going to be k over s minus a quantity squared plus k squared. And so what we have is it looks like this first part is going to be our cosine, and the second part is going to be our sine term. And so what do we want? Well, for the first one, we can bring out the 7. So I'm just going to do one extra algebra step just to make sure that it's clear where everything comes from. So I'm going to bring out the 7, and then everything else is fine. That's in the exact form that we want it. Here we want our numerator to be, if our denominator has a k squared term in it, that means that k must be 3. So we want this to be a 3. So what we'll do is we'll put a 3 there at the cost of multiplying by a third, and then we'll bring the 16 out as well. And now we have just a constant times what we're looking for. So remember that this was capital X, and so that tells us that little x of t is going to be the inverse Laplace transform. So this will be 7 times e to the negative 2 cosine of 3t plus 16 thirds times e to the negative 2t sine of 3t. And we're done.